Hello and welcome to another math video. Today we're going to be taking a look at identifying, graphing, and performing operations with complex numbers, and also finding complex number solutions of quadratic equations. First of all, what a complex number is. So complex numbers are really based on number whose square is -1. That basic unit is the imaginary unit I. So the idea there is that I squared is -1, and therefore also I is the square root of -1. So whereas with our just plain real numbers, we don't have an answer for a square root of a negative, so our complex numbers allow us to work with those square roots of negatives. So when we're talking about square root of a negative real number, so again here we're looking at a being a positive real number, square root of a negative a, what we do is we kind of reduce that radical per se. We pull out the -1 times a, and then we have the square root of -1, which is I. Now usually we'll write that as the square root of a times I, but either way, I guess we're not going to worry about it too much, so either square root of a times I or I times the square root of a. So the example they give is the square root of -5. Well, so that's I times the square root of 5. And again, we don't have to always go through all of that work. We can just kind of exchange the negative inside the radical for an I outside of the radical. And again, they go through kind of the work that they would have here for squaring a square root of a -5. So part of the reason we work with these imaginary units is because if we square them, we do get real number answers. So squaring a square root of a -5 actually leads to a -5 when we're considering the possibility of, again, complex numbers. And so writing the square root of a -18 using the imaginary unit I, again, all we really do there is it's the first of all, I times the square root of 18. And so then I still have to reduce that square root of 18 though. So we would do I and then the square root of 9, square root of 2. So that would be 3. So it's a funny looking 3. 3I times the square root of 2. Now typically you might leave it like that. I know some other people expect you to write it like this, 3 square root of 2I, and that has to do with standard form for a complex number, which we'll get into in a little bit here. Taking a look at these ones, so these are problems that, again, you could try on your own. If you want to pause the video and then do the problems and then restart when you're done, you can see what I have gotten for the answers as well. So if you want to go ahead and pause now, I'll go ahead and do these. So for A, we've got the square root of -12, so it would be the square root of 12 times the I, or I times the square root of 12. Now square root of 12 reduces using a 4, so that's going to be I and then root 4, root 3. And the square root of 4, of course, is 2, so 2I square root of 3, or in kind of the more proper way, 2 square roots of 3, and then the I at the end. Should be clear that the I is not inside the square root. That is important. B, that's just a plain old 5I, the square root of 25 being 5. And then C, it would just be I times the square root of 7, or again, more properly, square root of 7 times I. And if we look at part D there, explaining why the square root of -64 is not equal to a negative square root of 64. So what we have, if we simplify those, square root of -64 is 8I, whereas the opposite of the square root of 64 is -8. So those two things are not equal. So you can't just, kind of what we're trying to show there, you can't just pull a negative in or out of a square root. It's important that we, either we have our I's or we have our negative numbers, but you can't just say that those are the same thing. So complex numbers, I mentioned this just a minute ago, we can write complex numbers in this form, A plus B times I. A and B are real numbers. If B is 0, then this is a real number. Because if B is 0, and we show that here, then you just have a plus 0i. So all of our real numbers, again, they are really complex numbers. So real numbers are part of the whole big set of complex numbers. And they just happen to have nothing for their imaginary part. If a is 0 and b is not, then the number is what we call a pure imaginary number. So we show those here. So a 0 plus a bi, where b doesn't equal 0, because if they're both 0, then that would just be 0, which would be a real number. So 0 plus bi, a pure imaginary number, that'd be like 8i or 5i or negative 10i, whatever that might be. Other imaginary numbers that aren't pure imaginary have some value for a. So there's like a 3 plus 2i, 3 minus 5i, whatever that might be. But it has a real number part and a imaginary number part, makes it an imaginary number. So when we're adding or subtracting complex numbers, it's really as though the I were just a different variable, like an x or y, whatever you want to think of it as. We still just combine like terms. In this case, we've got 4 minus 3i and negative 4 plus 3i. Well, so again, here's another reason why we work with these complex numbers. And really we would have 4 minus 4 and then a minus 3i plus 3i. So everything cancels out and it's really 0. So we add two imaginary numbers together and we get a real number result. So again, so one reason why we work with these imaginary numbers. Now in example B, we're not going to have the same sort of thing. We'll actually have a 5 plus a 2, and then minus 3i, and then this will be minus 4i. So we get 7 minus 7i, and there we go. That's all we have for that one. And again, we've got some problems you could work on here at the bottom. So again, if you want to pause the video and work through them, then I'll go ahead and get started on them, and you can see what I've come up with. All right, so for A, we would go 7 minus 3, so that would be 4. And we'd have a minus 2i plus an i, so it would be minus I. Again, always running to write in the form A plus B times I. For B, we'd do 1 minus 3, so that would be negative 2. And 5i really plus 2i, so it would be 7i, because again, we're subtracting a minus 2i there. For C, 8 minus 8 would be 0. 6i, now this is going to be tricky. Some people are going to want to cancel that out. It's really 6i plus 6i, so we get 12i. So again, a pure imaginary number for that one. And the last one, we've got negative 3 plus 3, so that's gone. 9i plus 9i, so that would be 18i there. Hopefully you came up with the same things. Now multiplying complex numbers. We'll take a look at these again. Remember, I squared is negative 1. So if we get an I squared, we switch it to a negative 1. Okay, so for this first one, we would have a negative 15i plus 6i squared. Again, I squared is negative 1. I'm going to actually kind of switch the order there. So that's 6 times negative 1 minus the 15i. So it's really a negative 6 minus 15i. And again, notice I've switched it around so that it's in that pattern A plus bi. Looking at B, now it's a binomial times a binomial, so I would highly recommend using a 2x2 box for this. You could foil it, but again, this is where it's tricky enough where foiling maybe doesn't give you all the support that you need in order to be successful here. So the box, though, can kind of lay things out so you can keep track of everything a little bit better. And let's see, okay, so here I got a negative 6i squared. Well, that's really a positive 6 then, because I squared is negative 1. So I combine the negative 4 and the 6, and I get 2. And then a minus 3i and minus 8i gives us minus 11i. So 2 minus 11i is what we actually come up with there. Again, the box can be so very helpful, especially when you got some confusing things here. Now this looks a little bit interesting. We've got a negative 6 plus I and a negative 6 minus I. Seems like something special would happen here. So if we look at that, when we find our product, we get a 36 here, a 6i there, a negative 6i. Oh, look at that. Those cancel out. And a negative I squared. Now, I squared is really negative 1. We've got the opposite of that, so this is a positive 1. It's a funny looking one, but we'll go with it. 36 and 1 makes 37. So that just turns out to be a just plain old real number. So notice, take these imaginary numbers, you multiply them together, and the result is a real number. Again, that's part of the reason why we work with these. Even though they're not real numbers to begin with, they can become real numbers. Again, go ahead and try, pause the video, go ahead and try these, start it up, and I'll go through them as well. So for A, we get 21i squared, which I squared being negative 1 would be negative 21. I'd recommend a 2 by 2 box here. So 2 minus 3i, 4 plus 5i. Notice how a lot of these complex numbers are binomials, which I suppose increases the value of foiling, but again, still for me, I'll take my box over foiling any day. So this is really a positive 15 then. So 8 and 15, that gives us 23, minus 12i plus 10i, so minus 2i. And again, always in that standard form for a complex number, a plus b times I, which I've got right there. Hey, look, this looks special again. Negative 4 plus 5i and negative 4 minus 5i. Let's see what we come up with here. Again, pay attention to patterns as we're going through this. So we get positive 16, we get 20i, and negative 20i. Again, look at that, those cancel again. And we have a negative 25i squared, so that would be a positive 25. 16 and 25, we're talking 41 for that one. So again, notice that pattern comes up again, where the answer turns out to just be a real number. All right, so that brings us to the idea of complex conjugates. We actually just looked at a couple of examples of complex conjugates. And you can see they kind of play through the whole process here. Excuse me. A squared minus bi squared, which again gets us to here, the b squared, I squared. Really ends up just being a squared plus b squared. And so that's what we're looking at there. So a squared plus b squared is what we end up with as our shortcut to this. Now, reason this comes up so much is because we use complex conjugates in order to simplify quotients of complex numbers. So if I have something like a 2 plus 3i over 1 minus 4i like we have here, can't really do the division, but I can simplify it so that I can write it in the standard form for a complex number. Now, all I have to do is multiply by the conjugate of the denominator. Denominator being 1 minus 4i, the conjugate for that is 1 plus 4i. So 1 plus 4i. Again, we multiply top and bottom by the same thing. This is just a fancy version of 1. So we multiply top and bottom by the same thing. And we need to find our products. Again, the trick on the bottom, and if you want to box or FOIL this out, you can. Trick on the bottom is that it's just a squared plus b squared. So a is 1, b is 4, so it would be 1 plus 16. Squaring the 1, squaring the 4, there we go. So it's going to be a total of 17 for the denominator. Question is, what do we get for the numerator? I'm not really going to have room to put that there, but there we go. So then that's where we would box or FOIL this out. We're going to be doing plenty of that, so I think I'm just going to kind of figure this one out here. We'd have 2 from the, or maybe I'm not going to figure it out. I don't feel like doing that. Let's zoom in a little bit here, give me a little more space. Still making kind of a little box here, but okay. So 2 and the 3i, the 1 and the 4i. And so, okay, we got 2, we've got 8i, we've got 3i, and we've got 12i squared, which would be really a negative 12. So negative 12 and 2, we'd be talking negative 10 plus 11i. Now that's really over the 17. So what we do is we take that over the 17 and we actually just take each individual piece. Negative 10 over 17 plus 11 over 17i. Again, sticking to that a plus b times I format. Even though they're, fractions, still do the same thing. And then we do likewise with this one. Now here, we can actually get away with a lot less. Since the denominator is a monomial, we can get away just by multiplying by I. We don't have to use the complex conjugate. We can just use I. So then we get 9i on the top and a 12i squared. Well, the 12i squared is going to be negative 12 then. And then the 9i would just be 9i. Okay, I know I kind of went through that, but again, 9i, there we go, 12i squared, which is negative 12. So that's how we get that. We get a 3i squared on the bottom, which is really just negative 3. Divide each of those by negative 3. These actually divide nicely, so we get negative, or positive 4 minus 3i, what we're looking at there. Okay, zoom out a little bit here. And here we go. So here are 3 for you to try. If you want to, I'm just going to go ahead first and lay out the complex conjugate that we would use to multiply top and bottom. So if you want to see that quick before you get started, that's fine. If you want to go ahead and work through them completely on your own, go ahead and pause now. So here we would multiply by 3 minus 4i over 3 minus 4i. Here we could just do I. And over here we'd have to do 8 minus 7i. Now there's nothing mathemagical about that numerator there. It just so happens that the numerator is the complex conjugate for the denominator. So you'd still just set up a box like normal in order to find that product, or FOIL it, I suppose, if you really wanted to. So again, if you want to go ahead and pause now and work from here, that's fine. And I'll go ahead and work through these the rest of the way as well. So when we actually do our multiplication here, I'll just set up a box for the numerators. So it looks like that. Let's see here, as we fill that in, we'd have 15 minus the 20i minus 6i, and let's see, this would be a positive 8i squared, which would really be a negative 8 since I squared is negative 1. So 15 minus 8 gives me 7. And my i's are both negative, so minus 26i there. So that's the numerators. Again, the denominators, you can use that pattern where it would just be, if I can just sneak the denominator in right here, the a squared plus b squared. So it would be 3 squared plus 4 squared. So 9 and 16, we're talking 25 then for the denominator. Numerator still that 7 minus 26i. Now normally we would leave this alone because we wouldn't want to reduce it if it's not going to reduce nicely, but it's a complex number, or imaginary number really, and so we have to write that in the standard form for a complex or imaginary number. So 7 over 25 minus 26 over 25. That was weird. 26 over 25 I, and that's a funny looking 5. Let me make that a little bit better there. So that's a 5. There we go. And so that's what that looks like in the standard form for a complex number, and all of our imaginary number answers should look like that when we're done. Again, with B, if you know what you're doing, it's going to be a bit simpler. We just have to distribute that I across, and so if I do that, I get 4i minus an I squared, which again we can simplify really. I squared is a negative 1, so that would actually be a positive 1, and then plus the 4i, and then the denominator ends up being a 6i squared, which is actually a negative 6. So we would write that as negative 1 over 6, and you could put the negative on top, leave it on the bottom, whatever you want. Then minus 4 over 6, that's going to reduce. I'm just going to go ahead and reduce that now. 4 over 6 reduces to 2 over 3, and so we get that done. So negative 1/6 minus 2/3 I for that one. And here with this one, it might seem special, but really nothing super going on there in the numerators. We're just going to have to box that out like normal, so a nice 2 by 2 box there. Again, putting the 8 minus 7i on the left, 8 minus 7i on the top. And you could use the square of a binomial pattern if you really like that at this point. And of course, 7 times 8, everyone's favorite multiplication to get wrong, but that's 56. And of course, another negative 56. That's going to be a lot of i's. 49i squared. So that's really a negative 49. See, so numerator ends up being 64 minus 49 would be 15 minus 112i. Told you that was a lot of i's. So 112i. Now the denominator, again, it's that conjugate pair, so you can use that pattern, a squared plus b squared. In this case, that would be 8 squared plus 7 squared, so 64 and 49. Let's see, 64 and 49 would be 113. Surprisingly enough, that does not reduce. So 15 over 113 minus 112 over 113i. So there we go. I don't know why the marker's doing that stuff, but there we go. Okay. And let me just zoom back out again here so you can see the whole thing there if you want to just have a shot of that. All right, here we're looking at solving this equation. And kind of, spoiler alert here, we're going to get pure imaginary solutions. So, I suppose I should have had a sounder or something for that, but yeah. All right, so this is the solving where we just isolate the x squared term. So in this case, and they kind of have the steps there, we're going to isolate that, so we'll subtract the 32. And then we'll divide by 2. We get x squared equals negative 16. So at this point, we should be able to tell, okay, we're going to get imaginary solutions. We square root both sides, of course, square rooting x squared. And remember, plus minus, we got to remember that plus minus when we square root both sides of an equation. So we get x equals plus or minus, and square root of negative 16, that one should hopefully one of the easier ones for us that just turns out to be 4i. So there's, again, 2 imaginary solutions there, pure imaginary numbers, but those are the 2 answers for that. Again, the 2 answers, positive 4i and negative 4i. Again, you could give these 2 a shot if you want on your own, so if you want to do that, go ahead and pause, and then resume when you're done, and I'll be working through them. So let's see, part A here, we would subtract the 20. So we get negative 20 there. We would divide by 5. We get x squared equals negative 4. Ooh, thankfully, this one's going to work out well too. So we square root both sides. That really gives us the x on this side, and then positive and negative, square root of negative 4. And so we end up with positive and negative 2i. And there we go. So there's our 2 imaginary solutions. That wasn't too painful, now was it? Uh-oh, looking at B, I can already see what's going to happen there. So we would subtract the 15. That was supposed to be a 2. Subtract the 15. Negative 15 there. So we square it both sides. X equals positive or negative square root of negative 15. Now, we can, of course, take the I out of that. It's less painful than it sounds, but we just exchange that negative for an I. So we take the I out, square root of 15i. Now, if we could reduce the square root of 15, we would, but we can't, so we won't. And there's our 2 answers, positive and negative square root of 15i. Now this one, again, they kind of, spoiler alert, they tell us finding imaginary solutions again. But generally, we don't need to know that. We just look at the fact, okay, we got a quadratic equation. Sure doesn't look like it factors, so let's just go ahead and use the quadratic formula. And so, of course, then we need to identify the values of a, b, and c. We go ahead and we plug those in here. So if we do that, we get x equals the opposite of b plus or minus the square root. B squared would be 9 minus 4ac all over 2a, which would be 4. So there we go. That 4 should look less like a 9. There we go, 4. All right, so we've got the things plugged in there. And again, I am a big fan of just figuring out what b squared is right away. It kind of makes things easier, I think. Let's see. So we can do a bit more with that. So we have our 3. It's a 3. Okay, less like a 3. A little trouble with my pen today. 3 plus or minus the square root. Okay, so 9. This is going to be minus, let's see, 4 times 2 would be 8. Times 5 would be 40. So 9 minus 40, I'm just going to put that here. 9 minus 40. So negative 31. That is not a nice number. All right. Really not much we can do here. It's, again, the square root of negative 31 would be square root of 31i. So then we'd have to split that up. And of course I don't feel like doing both of those things, so I'm just going to split it and take the I out at the same time. So square root of 31 over 4i. There we go. So nothing pretty or fancy there, just that's what we end up with for our answers. There we go. Now, a couple here for you to try. Again, if you want to work through those on your own, you can go ahead and pause when you're Zoom. I'll go ahead and go through those as well. All right, so let's see here. My A is 3, B is negative 1, C is 2. So x equals the opposite of B plus or minus the square root. B squared is 1 minus 4AC all over 2A, which is 6. Okay, so 1 plus or minus square root. Let's see, so this would be 1 minus 4 times 3 is 12, times 2 is 24, so 1 minus 24, we're talking negative 23. So again, that's 1 minus 24, that's how we got that. And like I already said, the denominator 6. Again, not much we can really do here, which is actually kind of nice. You got 1 over 6 plus or minus square root of 23 over 6i. Now, again, just a reminder, it doesn't come up here. I don't remember if it did on the other one either. Yeah, neither did it there. 31 over 4 doesn't reduce, 23 over 6 doesn't reduce. Even if, those would reduce, we can't reduce that because, again, this isn't really 31, it's the square root of 31. It's not really the square root of 23, that is the square root of 23, my bad. It's not really a 23, it's the square root of 23. So even if those things would reduce, they don't really reduce because it's not just that number, it's the square root of that. So don't get caught by that mistake. Let's see, same sort of thing for part B here. I'm going to just scoot over a little bit. So A is 1, B is negative 4, and C is 5. Now, let's go ahead and plug that into the quadratic formula. So opposite of B, plus or minus the square root, B squared is 16 minus 4 times 1 times 5. All over 2 times 1, which is 2. Okay. Pen problems. X equals 4 plus or minus. Let's see, 16 minus 20. Oh, hey, look at that. We can do something with that. 16 minus 20. Again, that's where that came from. So this is 16 minus 20. That's what this is. Okay. Now, square root of negative 4. We take the I out. And again, less painful than it sounds. We get 4 plus or minus square root of 4i over 2. Well, so that then is really 4 plus or minus 2i over 2. And then we can actually divide those, so which we would have done anyway, since it's an imaginary number. But 4 over 2 is 2, and then plus or minus I. And there we go. Well, that is all that we have for Chapter 4, Section 8. I know it's quite a bit of stuff. Hopefully you found this video to be helpful, and certainly if you have any questions, feel free to let me know. Thanks for watching.